So the final topic I wanted to discuss in this course, which indeed is a chapter in the book, is about first order phase transitions. And so I show here the kind of standard phase diagram of water that I've already shown a bunch of times. And if you see that plotted on Wikipedia, that's the way it's usually plotted, that one axis is temperature and the other axis is pressure. Of course, as you change the pressure of the gas, you change its density. So in principle, it could have been plotted as a function of density instead, and it would look very similar. So these lines that you see there are all what we call first order phase transitions, because even though the pressure of the two phases is the same, that's the only way that they can mechanically be in equilibrium. You have some kind of interface between the two phases. They must be at the same pressure. But as you go from the vapor to the solid or the liquid, the density changes discontinuously. And that means a number of other thermodynamic quantities have to change discontinuously as well. So there's one point where a bunch of these first order phase transition lines meet. That's usually called the triple point. So that's a point, obviously, where you can then have three phases in contact. So this one, sometimes called the triple point. And the other signpost that we already talked about previously is the fact that the liquid vapor transition actually does end. So there's a liquid gas endpoint, and beyond that, you can continuously go from the vapor to the liquid. Okay, so there could be a first order phase transition between liquid and vapor, or there could just not be a phase transition. And both of these are realized. It's just just a question of the temperature at which you're looking. So, so if you go through that phase transition, which of course you do all the time. So if you boil water on your stove, you go through that first order phase transition. So generally, we do that in the direction which is not the direction that I plotted here. What I now plotted is that at fixed temperature, I change the density, but we'll visit the other one in just a second. So here, what I show in this yellow line is we imagine the temperature is fixed, and we're just compressing or expanding the system. So then you go from a low density phase, which is vapor, to a high density phase, which is a liquid, and in between, there's a discontinuity. And so what that means is that if you plot the same thing, but now you plot it, say, with the volume of the system on the x-axis and the temperature of the system on the y-axis, okay, at some constant, then this transition that I just showed, that must somehow be a transition. Again, at a fixed temperature, you go from some system at high density, so small volume, to some system at low density. Okay. So this is this transition. So if I plot the arrow in the same direction, it would be going this way. Okay. So so since the density jumps, it means that so these are all completely physical states. These are completely physical states in the vapor phase. Okay. These are perfectly physical states. They're in the liquid phase, but the states in between, they don't really occur. So there's a kind of forbidden region in density, because at the first order phase transition, the density jumps. Okay. This forbidden region will disappear above the liquid gas endpoint. So there's some kind of region with a shape that looks something like this. And that region is not truly forbidden. Obviously, you can just take a system and dial in a density by just having a certain number of particles, and you change the volume. That you can obviously force it to be there. So the question is, what exactly happens in this regime? Okay. So what happens if you take gas and liquid, and so there's a gas phase at a low density and the liquid at the high density phase? What happens to the system if you force it to keep it, if you force it to have densities that are somehow in between, and if you think about this for 30 seconds while I write down what this is called. And indeed, it's a phenomenon that you see all the time. If you actually boil a liquid, then it doesn't just sort of spontaneously, you don't have a pot of water and it spontaneously changes to all gas. What you see appear is you start to see bubbles appear. So the way that you can have systems in this coexistence region is that the mean density is in this forbidden regime, but the way the mean density is realized is that we have bubbles of the low density phase inside the high density phase, or the other way around. So if you come from the low density side, then what appears are bubbles of the high density system. And at the other end, what you get is bubbles of the low density phase inside the high density phase. Okay. So this is the low density side, and this is the high density side. Okay, and both of these occur in this coexistence region. And now, of course, I kind of plotted them backwards. So so this here is the high density side of things, and this here is the low density side of things. Okay. And then purely vapor, of course, is purely gas, so then there's no more coexistence. And purely liquid is pure liquid, again, no more coexistence. So, so what happens in this coexistence region where you're in the kind of forbidden regime, the forbidden regime is not truly forbidden, it's just forbidden for a homogeneous substance. What the system actually does is it phase separates into bubbles of the low density phase inside the high density material, or the other way around, okay, depending on what density you are. So the question is how to describe the system in a situation like this, okay? So observation number one is, so far, the sort of generic, the default thermodynamic function that we've used was the free energy. So if in doubt, we generally use free energy because it's the logarithm of the partition function. So the free energy is a function of the temperature, the volume of the system, and the number of particles. And that's a perfectly good thing to look at, but the disadvantage that it has is, so if you use these variables, V and M, then you encounter this kind of coexistence region. But if instead as a function of volume, you plotted it as a function of pressure, which was kind of the first plot that I showed, then there's no coexistence region. There's just a line where everything jumps. So if you perform this kind of Legendre transform, to a function that's a function not of volume, but of pressure, and that function we've already encountered, it was called the Gibbs free energy. This is a function of T, P, comma, N. Then that same transition does not have a coexistence region, it just has a discontinuity. So there's a line of phase transitions. Okay. So we will eventually get back to this question as to how to describe the coexistence region. But for now, we will indeed look at the Gibbs free energy because, okay, that helps us to figure out where that happens in the first place. So we look at this Gibbs free energy. Okay, so Gibbs free energy is a function of three. So number one, it was a Legendre transform. So Gibbs free energy as a function of T, P, and N is free energy Legendre transform. So free energy was E minus Ts. And to Legendre transform from volume to pressure, we just have to add plus PV. Okay. So this is the definition in terms of a Legendre transform, but that expression can actually be simplified because we had this extra relation that followed from the homogeneity of entropy, which was that E plus PV is mu n plus ST. So we've used that a number of times. We've used it, for example, and you have a practice problem for that as well. We used it to reconstruct the pressure of a free Fermi gas from its energy density intensity. Okay, that's one of the places where we use this. So this implies that Gibbs free energy in the end, G of T, P, comma, N is actually just equal to mu times N, because E plus PV is mu N plus ST. So if I subtract the ST, then all that remains is mu N. Okay. It's a function of T, P, and N, which means that there must be suitable partial derivatives. So there must be some relation of this form that dg is something dt, something dp, and something dn. So the corresponding partial derivatives are just entropy, volume, and chemical potential. The only thing that's not so obvious is the signs, which again, you can just write down on your little sheet that you bring to the exam. Plus mu dn, okay? So this means, among other things, that if I take a partial derivative of g with respect to t, and I keep the other variables constant, then what I get is minus s. Okay, that's one of these partial derivatives. Okay, so the question is now what happens with this Gibbs free energy at a phase transition? Okay, so just to remind ourselves, the Gibbs free energy was a function of the temperature, the pressure, and the number of particles. So at a phase transition, so we have this magic again. We just remind you of the plot. So here's P and here's T, and there's some kind of phase transition line in this plot. Okay, here we are. There's a phase transition line. So, so at the phase transition itself, the pressure on both sides of the phase transition is the same. That's A, clear from the way it's plotted, because it's just a line, there's no coexistence. And number two, that's just mechanical stability. So if I have a high density phase in contact with the low density phase, the only way that interface can be stable is if the pressures on both sides are the same. Otherwise, the bubble would have to grow or shrink. So there's a liquid and a vapor phase, and they must have the same pressures. Okay, so this is, if you wish, mechanical stability. Okay, but the Gibbs free energies must actually also be the same. One way to see this is because, as we saw on the previous slide, Gibbs free energies at a fixed number of particles is just chemical potential. And again, that was one of our equilibrium criteria. If you have two systems that are in contact with one another, then chemical equilibrium means that they must have the same chemical potential. Otherwise, particles would go from one phase to the other. So the Gibbs free energies of these two phases are also the same. Okay, so the left is the liquid phase, and the right is the vapor phase. Okay, so what does that mean if I now try to plot, say, Gibbs free energy as a function of temperature? So I imagine that I'm now looking at this object. So there's the Gibbs free energy, which is a function of three variables, but it is plotted as a function of one, keeping the other two fixed. Okay. So as a function of temperature, this is now actually going kind of this way. Okay. As a function of temperature, I eventually encounter this phase transition line. Okay, so there's some Gibbs free energy, and it's doing God knows what. Okay, doing something. And then eventually I encounter this phase transition. So how does the function continue at this point? Well, the Gibbs free energy of the two phases is the same. So the function cannot jump at this point, okay? But there must be some non-analyticity because there are things that do jump, like the density does jump, and the density is, density is related to volume, so density is some kind of derivative of Gibbs free energy. So for derived quantities like the density to jump, there must be some change in slope of the function at this point. So there must be some behavior like this, say, okay? So that at the phase transition point, this is the critical point for the phase transition, at the critical point, again, the function itself must be continuous. That's the function g itself cannot jump, but the derivatives in general do jump, okay? And one of the things that you can imagine, and we'll see that indeed this physically does happen. So this sort of looks like an intersection line of two functions, that there's one function coming in and then it continues as some other function. And at the phase transition, these two functions just simply intersect. So you can imagine that really these are two functions, okay? And at the phase transition line, they intersect. So what could be the meaning of that? So number one, so again, what we plotted here is, so the low temperature side, that would be the liquid side. So this is the Gibbs free energy for the liquid, okay? This here is the Gibbs free energy of the vapor. Okay. So what could be the meaning of these kind of dotted lines where I just naively continue? So the dotted lines are a liquid that somehow exists beyond the phase transition. So this is some kind of superheated liquid. And the other one would then analogously be some kind of supercooled vapor. So by supercooled or superheated, we simply mean it's kind of the wrong phase. We somehow managed to continue the wrong phase just a little bit beyond the phase transition temperature. And you may have seen these kinds of experiments. So if you do that with water and you do it super carefully, you can indeed do that. You can get the liquid phase to continue just a little bit beyond the critical temperature. So if there aren't any kind of impurities in the system, if you keep it mechanically very stable, then indeed you can generically superheat just a little bit, and you can try to carefully measure the Gibbs free energy. And that will indeed be this curve. What this also an illustration of, by the way, is that we saw that if you have sort of more than one phase or more than one option of your system, the thermodynamically stable one is the one that minimizes free energy or Gibbs free energy. So one way to think about this is that there are two possible functions, the Gibbs free energy of the liquid and the Gibbs free energy of the vapor. And the thermodynamically stable one, the one that's shown as the solid line, is just the minimum. Okay, so the stable phase is the one that minimizes Gibbs free energy. Okay. So again, that's this idea that there are, in your plot, we saw there's two lines. Okay. And what the system really does, it follows the one that's the lower of the two. So the thermodynamically stable situation is to follow this line. Okay. So one of the things we see from this is, again, I go back to the plot. So our plot was Gibbs free energy as a function of temperature. And the Gibbs free energy itself didn't jump, but the slope does. Okay, something like this. So, so the slope is indeed something I already wrote down now on an earlier slide, because the slope in this plot is just dg by dt at constant pressure and particle number. And what I wrote down on the previous slide is that this is the negative of entropy. Okay. So if the slope changes, that means that not only the density changes discontinuously at the phase transition, but the entropy changes as well. Okay, so there's a discontinuity in entropy. Okay, and the change in entropy, so the high temperature phase is the one with the higher entropy, and that's indeed how I drew it. That's the one with the steeper negative slope. So, so the change in entropy is minus dg by dt in the vapor phase minus dg by dt in the liquid phase. Okay. And so what is amusing is that I can compare this to this kind of thermodynamic definition of entropy we had when we introduced it, sometimes called the Clausius definition of entropy. And that came up when we analyzed these heat engines, which again, kind of historical origin of entropy. And there we related changes in entropy to irreversible heat flow, okay? So, so there was a kind of thermodynamic definition. And that definition was that delta S is delta Q divided by T. So now that I have a formula for delta S, I can write one down for delta Q. So I get a formula that delta Q is T delta S, so that's minus T dg by dt in the vapor phase, dg by dt in the liquid phase. Okay. So physically, what is this? So there was a change in entropy, and in order to get the entropy to change, we have to add heat to the system. Okay. So what is that kind of heat? That has a name. So the amount of, so previously we introduced something we called specific heat, which is the amount of heat required to change the temperature of the system by 1 degree Kelvin. Here we sit at a phase transition, and so the temperature is actually the same. So we sit at constant temperature, we sit at this discontinuity in the slope, but even though the temperature does not change because there's a discontinuity in the slope, the entropy does change. So I'm adding heat at constant temperature. I'm adding heat to the system, not changing the temperature, but I do change the system from one phase to the other. So this object is called latent heat. So this is called the latent heat. And the way it's defined in our book is that the latent heat is defined per particle. So this is called L times N, where N is the number of particles. So this is an idea that in principle you of course encountered in kind of undergraduate or high school physics, that, and indeed you see it every day when you boil water on the stove, that, so you put the water on the stove, it takes a couple of minutes for the bubbles to form, but then of course the water does not instantaneously disappear. In fact, you can leave it on the burner for a long, long time, and it just slowly converts water liquid to water vapor. And the reason it takes so long is because the latent heat of water is actually pretty darn high. The latent heat of water is numerically a lot larger than the specific heat to change the temperature by a degree or two. So it takes a lot of latent heat to convert water completely into vapor at conditions where you're not actually changing the temperature at all. Okay. So this is one thing that in principle you've probably encountered before as an undergraduate somewhere. Okay. The other thing that I wanted to remind you of, which you've probably also seen before, is something called the Maxwell construction. Okay. So let's again start from the plot that I already showed a couple of times. So this was the original plot that I showed, pressure and temperature. Okay, and there's a bunch of transition lines. Okay. And so, so now we previously plotted this as a function of volume and temperature. So I previously showed some kind of plot like this. And there was a forbidden region somewhere. So that was this coexistence region. And so now I want to show a slightly different plot, which you often see, which is pressure as a function of volume. So not temperature as a function of volume, but pressure. Okay. So this is usually something called the equation of state, that you imagine that you have it at constant temperature and you compress, you want to know how the pressure changes. This is usually called the equation of state. Okay. So again, question is, what does that look like? So generally, for a mechanically stable system, the pressure must increase as you compress. So there must be something like so. So you make the volume smaller, the pressure increases. Actually, I mean, maybe just as a side remark, why is that so? Okay, imagine you have some kind of system again in a container with some kind of barrier that can slide around. Okay, so so if the system is in equilibrium, then you have gas at some pressure P, gas at the same pressure P. If the pressures were not the same, then the partition, if it's a sliding partition, then the partition could not stay in place. So now imagine you displace that partition ever so slightly. Okay, it moves, by some random fluctuation, it moves to the right a little bit. Okay, what we expect to happen is that if you make the left volume a little bit bigger, then the pressure drops. Okay. And here the pressure increases. But that, of course, is precisely what is needed to restore the system to its previous state, because now the pressure on the right is a little bit bigger and the pressure on the left is a little bit smaller. So that will give you a force that pushes the divider back to where it came from. So that means that if you have a container that separates two gases at the same pressure with some kind of sliding partition, for a gas that behaves in the expected way, that partition is somehow stable. It doesn't just suddenly explode. But if you're in the wrong regime, if that has the wrong sign, and you make the partition slide a little bit to the right and the pressure on the left increases, then it would slide even further, which means that this system would be somehow subject to spontaneous combustion in some way. It would tend to somehow explosively decompress or something. Okay, so stable systems have a pressure that increases if you decrease the volume. So in this phase transition, again, where the small volume limit is the high density limit, so that would be some kind of liquid, and eventually you encounter the phase transition. And on the other side of the phase transition is a system that's at the same pressure, again, that's mechanical stability, but at a different density. Okay. And again, beyond that, it will somehow behave like a normal gas. It'll have some equation of state that looks like this. And in between, again, there must be some kind of forbidden region. So this is in between, there is a region which is not truly forbidden, but where you have phase coexistence. Okay. And so roughly what Maxwell observed is that, so physically what the system does in the phase coexistence region is, again, physically it forms bubbles, and all of that must happen at constant pressure, because again, otherwise the bubbles could not be in equilibrium with, you know, the medium that they're embedded in. So the physical system goes to phase coexistence as a straight line. However, we saw that you can typically take the low density or the high density phase and continue just a little bit further. That was this plot of continuing the lines in the Gibbs free energy just a little bit further. Okay. So, so if I take that idea seriously of continuing these lines, okay, let me find a color to continue them in. Let's this one. So then you would continue to keep going here. So we just follow this line for a little bit longer. And the same with this one, you can follow this line for a little bit longer. And eventually that becomes unphysical. And the way it becomes unphysical is that, for example, the slope of pressure versus volume now eventually becomes incorrect. So it becomes incorrect, it would start to increase. So that would be an unphysical system. Okay. And so what you can then imagine is that indeed there is just kind of one line. Okay, let me blow this up. So this is what I just drew. Again, this is a phase diagram of pressure versus volume. There's my coexistence region. So there's 2 points that are connected by a phase transition. Okay, what I now suggested is some construction where there's a line that comes down, eventually becomes unphysical, but maybe it hooks up with this one, which is also physical. But what the actual system does, it goes through there but via phase coexistence. So the real system goes through here as a straight line. Okay. And we'll see in a little bit, I'll show you an example. It's actually already posted on the Moodle site, is there are indeed sort of actual equations of state that have this kind of funny behavior that originally you have the correct behavior of the pressure, and then there's this little loop-de-loop, and then it again becomes physical. Okay, so an example for this is something called the van der Waals equation of state. Okay, so so what Maxwell observed is the following thing. So imagine that you indeed have this magic curve. You have a, what I would call a van der Waals type of equation of state. Okay, then what you actually have is some kind of plot that looks like this. Okay, so you have this funny equation of state, which looks like so. Okay, so this is what is shown on this plot is this axis is pressure, this axis is volume, and this curve is some constant temperature. Okay, and if you had a different constant temperature, you would have some other curve that looks like that. But if the temperature is higher, then of course the pressure is a little bit bigger. And if the temperature is lower, then it looks like this. Okay. So, so if you have a series of curves like this, then you don't actually know where exactly the phase transition occurs. I mean, the only thing you truly know now is that there's a there's a truly mechanically unstable region. Okay, so we know that these regimes are certainly unphysical because, again, it has the wrong behavior. Okay, so this is mechanically unstable. But the correct behavior of the system, after all, is to go from here to here. But the question is, just by looking at that van der Waals equation of state, how do I figure out exactly where these 2 points are? Okay, so that's the question. So where means, say, what pressure and what volume. Okay. So one way to figure this out, which is in some sense ultimately what we're about to do, is that you can also compute, once you have the pressure as a function of the volume and the temperature, you can always, by thermodynamic formulas, reconstruct the Gibbs free energy. And we know that these 2 points, the 2 green dots, they must not only sit at the same pressure, they must also sit at the same Gibbs free energy. So what I can somehow do is find all candidate pairs of points on this curve that have the same pressure, so they sit at the same height, and also compute their Gibbs free energies. And if their Gibbs free energies also match, then these are the correct endpoints of the first order phase transition. So in principle, I could do that, but that seems a little tedious. And effectively what Maxwell suggests is a kind of shortcut. Okay, so in principle, so we wish to determine where this point is. So this is a question mark. And in principle, that can be answered by observing that they must have the same G. Okay. And so we can now formalize this in the following way. So we had this magic formula for differentials of G, which is that Gg is minus S dt plus V dp plus mu dn. Okay. So what that means, among other things, is that if I look at this formula at constant temperature and particle number, so these are, the black lines that I drew there, they're isotherms, so these are at constant temperature. So this formula implies that dg at constant temperature and the constant number of particles is V dp, okay? So I can take this relation and now just integrate it. Okay, I just wrote down that dg at constant t comma n is V dp, and I can integrate that. So I get the integral of dg is the integral of V dp, okay? But if I integrate this from the 2 endpoints, the 2 endpoints are the G in the liquid phase and the G in the vapor phase, okay? And here, the 2 endpoints are the P in the liquid phase and the P in the vapor phase. Now, what you see from this is these are actually the same. I mean, the G in the liquid phase and the G in the vapor phase is the same. So this integral is actually just 0, okay? So in principle, this is 0 equals 0. But let me just write down the 0 on the right. So okay. So why do I write down the 0 on the right is because if you follow that, looping line in the coexistence region, the volume actually does still change. Again, let me show this plot again. Okay. So this was our equation of state. It was pressure as a function of volume. Okay. And we had some kind of curve, like so. So you see that even if I make a transition here somewhere from some endpoint to some endpoint, that even though the pressures are the same, the volume continues to change. And that's maybe even more apparent if I take that plot and I just rotate by 90 degrees. So if I take that plot and just rotate, okay, so then I have a plot with this pressure on this axis and volume on that axis. So, so sadly, this is now on a computer. If I had it on a sheet of paper, I would just take that piece of paper and fold it over. So now I have to think what this looks like. So at large volume, the pressure is small. And so then it does something like this. It loops and goes like that, okay? So again, I just rotate it by 90 degrees. Okay. And so what this formula is saying is that as I do this looping, this integral VdP, which in this plot is now just the area under the curve, must be 0, okay? Now the area under the curve is a little bit of a funny thing because the trajectory that I'm taking is a trajectory like this, okay? So I start here. Okay, so this is my integration trajectory. So what happens if you follow this integration trajectory? Again, let me maybe plot it one more time. So let's get a new whiteboard and see if I can reproduce that plot one more time. Okay, blow it up a little bit. So in this plot, this is now what I call V, this is what I call P. And I had some kind of curve that looks like this. Okay. So I have a starting point and I start to integrate. Integrating means the area under the curve. So I'm just taking all the area going down. In principle, I'm going all the way down, but since I return, I'm adding up area and then I go back, so I subtract it. So really effectively, I'm just adding up this area. And then I go on the other side. So again, I start to compute the area below the curve. In principle, it's the area all the way down, so including here. But since I'm about to reverse myself, okay, it's really only the area between the curves. Oh no, now I destroyed it. So it's this area plus this area, okay? And that was this magic integral VdP that's ultimately equal to 0, okay? So based on the endpoints, it's trivially 0, but if you actually do it following this equation of state, the van der Waals type of equation of state, it suddenly becomes a non-trivial statement. And so effectively, this is an equal area rule. So the way this area is effectively 0 is, of course, that you accumulate the initial area, the one up here, with kind of a plus sign, and the area here with the minus sign, because you're going backwards as you're doing the integral, okay? And so this integral being 0 is some kind of equal area rule, that you have a positive area and then you have a negative area. Okay, so now that I have the equal area rule, I can go back to my original plot. I can plot pressure as a function of volume. Okay, I had an isotherm. So what is called the Maxwell construction is that as I'm trying to figure out how to go across, so in principle, I have all sorts of possibilities to go across here. The correct way to go across is the one that gives me the equal area rule. So the correct solution is this one because it equalizes this area and this area, okay? So this is called the Maxwell construction, that in an equation like this, the way you find the correct endpoints to the phase transition is that you take a ruler and you slide it up and down until you have equal areas on the left and right, and then your ruler will intersect the endpoints of the phase transition here and here. Okay. And so it was, again, originally discovered by Maxwell in connection with the liquid gas phase transition in water, but it's, of course, again, more general than that. So it applies to all first order phase transitions in statistical mechanics. And indeed, it actually applies in many other physical systems as well, because it's actually not so uncommon that you have some phase of matter and it's described by some kind of multi-valued function. And then you have to somehow figure out what the correct possible equilibrium states of the system are, okay? And I have a notebook that shows a sort of numerical example for this kind of procedure, which I can show you maybe at the end of the lecture, because if I go away from the whiteboard now, it makes it hard for me to save the whiteboard. Okay. So, so this is this Maxwell construction. The other thing I wanted to briefly address, and that's something we already looked at in the homework effectively, is sort of how does it actually happen? So what I mean by that's the following. In this coexistence region that we can now, with the help of the Maxwell construction, we can somehow find the endpoints of the coexistence region. And we have this phenomenon that, you know, you come from the liquid side and the way the gas first appears is as bubbles, okay? Okay, so that's somehow how it actually happens, how you get into this coexistence region. You put your pot of water on the stove, you start to heat, eventually you see bubbles appear. And people started to wonder, I mean, number one, so these bubbles obviously have an actual size, you know, what determines what the size of the bubble is, what determines at what kind of temperature you first see a bubble. Does it have to be exactly the phase transition temperature, or do they start to appear maybe a little bit earlier than that? Like, could it be that even if you're not exactly at TC yet, there's some probability to see a bubble, but they tend to recollapse, which is indeed exactly what you have. What happens is that below TC, you start to see a few bubbles appear, but they tend to recollapse. And then as you get to TC, these bubbles effectively become stable, okay? So, so the question is whether we can answer these kinds of questions. What kind of bubbles, how stable, what is the probability that they appear, and so on, okay? So for that purpose, I want to go back to this kind of diagram. So what we showed is the Gibbs free energy as a function of temperature. And in this plot, okay, we had the situation that the Gibbs free energy does not jump, but the slope changes. So, so this is, again, this would be the low temperature phase, which is the liquid. Okay, and this is the vapor. So you can go in either direction. So for example, let me continue a little bit into the high temperature phase, okay? Okay, so you continue a little bit in the high temperature phase. So we're at some temperature that's above TC. So in principle, the system is all all vapor, but maybe occasionally there's still a little bubble appearing, okay? So what you see from this plot, that if you sit at some temperature that's, delta T above the phase transition temperature, then, because the slopes are different, there's now a difference in free energy between these two curves, okay? So one was the continued liquid curve, the other one is the physically stable vapor curve, okay? And this delta G, of course, is simply determined by the difference in slope. So this delta G is just delta T times the difference in slopes. So, so the lower of these curves is the vapor curve minus dg in the liquid. Okay. Actually, did I do it the right thing? I think I did it the wrong way. So if I take the difference between the upper curve and the lower curve, then this is the liquid and the other one is the vapor. Okay. So, but we saw that these derivatives, they're just related to the entropy, and we previously related the entropy to the specific heat, to the latent heat. So this can also be written as delta G is delta T times the liquid, times the latent heat, times the number of particles divided by the temperature. Okay. So if you form a bubble of this stuff, then that costs a certain amount of Gibbs free energy. And the Gibbs free energy that it costs is related to the delta T where you want to do it, the latent heat, and the number of particles in the bubble. So if you want to form a bubble of some size, so you have a bubble of some radius r, then the number of particles inside is just going to be the density of the system times the volume of your bubble. So this is going to be rho times 4 pi over 3 r cubed, because this is just the volume. So density times volume is the number of particles in your bubble. Okay. So the Gibbs free energy cost is then forming a bubble is delta G is equal to delta T latent heat divided by temperature times the number of particles in your bubble. So that was density 4 pi divided by 3 r cubed. Okay. So so making the bubble then has some probability. Okay. So that probability will be, since again, free energies are sort of Boltzmann factors, so that probability is just simply e to the minus delta G over K Boltzmann T. Okay. So so what is the sign now? So if you're in the wrong phase, then you always lower the delta G in order to go into the right phase, okay? So if you're somewhere in the wrong phase, sorry, what do these curves look like? So the curve looks like this. Okay, so in this case here, delta G is less than 0, okay? So you somehow accidentally continued in the wrong phase. And to get to the right phase, that lowers the Gibbs free energy. Okay. So this means that the probability for this to happen is e to the, plus delta t times r cubed times, various other factors. So, so if you somehow accidentally continued in the wrong phase, then you can always lower the Gibbs free energy. So if you make a bubble of any size, then that has a large probability, and the probability gets bigger and bigger the bigger the size. So that says you somehow kind of instantaneously jump into the other phase. Okay, the faster the better. But again, what we know empirically is that it's not quite how it happens, that you can actually superheat the liquid a little bit before it eventually, if you just do it carefully enough, you can always superheat a little bit. So, so there's some mechanism that actually obstructs the formation of bubbles. And so in the real world, bubble formation is inhibited by the fact that to make a bubble costs some amount of surface energy. So in practice, okay. And that is actually, I'll show that again in a little bit. That was our little exercise in the easing model, that you can actually try to measure in numerical simulations what that surface energy cost is, okay? So in practice, what you see is that this delta G has a term that makes it bigger, and that's proportional to the area of the bubble, minus the term we just computed, so minus the thing that wants to lower it. So there's okay. So in this formula, this is some kind of surface energy. Just on dimensional grounds, it's a surface energy because Gibbs free energy has the same units as an energy. So sigma is an energy per unit area. Okay. Again, this was the volume. So this formula then is something like this, that so delta G is sigma, a surface area is 4 pi r squared, and then we had a term that's negative, and it goes as delta T over T as latent heat times density, and then there was the volume 4 pi over 3 r cubed. Okay. So this thing, you can try to plot it to see what it looks like. So delta G is a function of the bubble size. So for small bubbles, it's this r squared term that wins, and for larger bubbles, it's the r cubed term. So originally this goes as r squared with the positive sign, so it costs Gibbs free energy to make a bubble because of surface energy, but eventually this r cubed term will win. So this is effectively kind of surface energy. And this is volume energy. Okay. And so the magic point in this curve is kind of the point at the top, because so this is some kind of critical radius. Because if you sit to the left of that point, then bubbles, it's more likely for the bubble to collapse than to grow, because you can lower the Gibbs free energy that way. Okay. So, so in this regime, bubbles will have a tendency to collapse, and in this regime, bubbles will have a tendency to grow. Okay. It doesn't mean, by the way, that every single bubble of that size has to shrink. Again, this is all a thermal system, there are fluctuations. It just means that it's more likely to collapse than to grow. And so in this regime, bubbles grow. Okay. And so we can obviously compute where that happens. So this magic red point is simply the point where the derivative of delta G with respect to the bubble size is equal to 0. So that's 8 pi sigma r minus delta T over T. So that was a T. Times L rho 4 pi r squared. When that's equal to 0, that determines the critical bubble size. So the critical bubble size is then R critical. So it's R squared is equal to R. So this whole thing is just linear in the surface tension. 8 pi divided by 2 pi is just 2. So this is 2 sigma times T divided by delta T divided by L and divided by rho. So this is the critical bubble size. Okay. And it goes as 1 over delta T. So is that the right way around? The critical bubble size will go inversely as delta T. Yeah, I think that makes sense. And you can also then compute what is the corresponding Gibbs free energy. So what is the Gibbs free energy at RC? So that should scale as sigma r squared, or as delta T times r cubed. So at the critical size, these two terms should be the same order of magnitude. So r squared will go as sigma squared T squared. So this will go as sigma cubed T squared divided by delta T squared divided by L squared and divided by rho squared. And so this is the Gibbs free energy required to make a critical size bubble, so one that's likely to grow. And so the final thing you can then say is, so what is the probability for this to happen? So what is the probability of forming such a bubble? So that's proportional to e to the minus delta G at the critical bubble size divided by T. So that's proportional to, so the magic delta G again had the scaling sigma cubed T squared. So this one will go as sigma cubed T squared divided by delta T squared and divided by the latent heat squared and divided by the density squared. Okay. So, so as you get closer and closer, it's more and more suppressed. So this is indeed saying that you can superheat just a little bit, because if you superheat just a little bit, delta T is small, and it's actually unlikely that you form a bubble. But if you go further and further away, then it's easier and easier to nucleate a bubble. So as delta T increases, it gets easier to nucleate a bubble of the right phase. Okay. So, so let me maybe just show you, unless there's sort of immediate questions about this. First of all, let me save this. Okay. And then I can maybe show you a couple of things that are also posted on the Moodle site. So let's go to Moodle. So the first thing we talked about today was this business with the van der Waals equation of state. Where did that now go? Oh. Somewhere. Ah, okay, that's not what I want. So here it is. So this is this equation of state that we actually encountered in this quiz the other day. And so the equation of state, here it is. So it's the regular ideal gas equation of state, which would have been PV is NT, but there are kind of two corrections. Number one, the effective volume is kind of corrected by this excluded volume factor so that every atom takes up a certain amount of space. That was this parameter B. And the effective pressure is shifted by a term that goes as density squared, which loosely, so here the pressure is lowered by some amount that's proportional to density squared. And you can think of this as attraction between the atoms lowering the pressure. So both of these coefficients A and B are taken to be positive. So every atom takes up a positive amount of volume. That's excluded volume that will tend to increase the pressure because there's less space for the atoms. And the other term tends to decrease the pressure the atoms attract. Okay, so that's really, by the way, what's sort of generically required for a liquid gas phase transition is a sort of competition between attraction and repulsion. It's the attractive terms that somehow want to make something like a liquid phase, and it's the repulsive terms that eventually stabilize that liquid. Okay, so so the first plot is just a bunch of isotherms, which are sadly not labeled. So this axis is pressure, and this axis is volume. Okay, so if you do it at very high temperature, by the way, then indeed you're above the endpoint of the liquid gas phase transition. So you don't see this kind of S-shaped figure in this case. But if you go to lower temperatures, then the sort of S shape appears. Okay, and so a priori, it's not clear how we go across this. So where's the coexistence region? And I already mentioned that one of the ways to figure this out is to compute the Gibbs free energy. Okay, that's effectively also an exercise that was sort of implicitly contained in this quiz we did the other day. So you can work out what the Gibbs free energy is. So here for a given isotherm, I plot the pressure and I plot the Gibbs free energy. And then what I want to find is a point where for two different densities, so for two different values along the x-axis, both the pressure and the Gibbs free energy are the same. Okay, so one way to find that point is to parametrically plot as a function of the density or the volume of the system to both plot the pressure and the Gibbs free energy. And so this is again plots that effectively I showed earlier. So I plot the Gibbs free energy as a function of the pressure. And again, effectively the way I did it is by parametrically plotting the pressure and the Gibbs free energy. And this is this magic curve where you see a change of slope. So there's a high pressure curve that comes in with some slope, and here it becomes unstable. The correct curve is the lowest slope. And you see that in this van der Waals model, there really aren't two curves. There's just one curve that first goes this way, then it retreats, and then it goes down that way, and it self-intersects. And it's this self-intersection point, which is the point where you have two different phases where both the pressure and the Gibbs free energy are the same. So one of the ways to find the coexistence region is to locate that point, okay? And in this kind of parametric plot, you can actually just look at it and see where it is. It's located at some pressure, which on this plot, the pressure is 0.23 and the Gibbs free energy is minus 0.12 or something like that. Okay, but then I can verify that this point can also be found by the Maxwell method. So here actually just, by the way, numerically determine the coordinates of that point where the two curves intersect. And now I show the Maxwell construction. So the Maxwell construction is I take whatever two densities that I now found, so there's a low density and a high density, and I can now just connect them by a straight line. And this is now the coexistence region. And according to Maxwell, it must be true that this area is now the same as that area, okay? And I can just check that by numerically integrating the difference between the pressure of the van der Waals curve and this yellow line, which is the pressure at the two coexistence points. And if everything is fine, this should integrate to zero. And here's where I carry out that integral going from the left endpoint to the right endpoint. And indeed, you integrate, and it changes sign, so you integrate back to zero. And indeed, on the other side, the value of the integral is exactly zero. So these areas, which is maybe not immediately obvious, these two areas are indeed the same, okay? So that's one thing that's plotted. And the other thing I just wanted to remind you of, which we looked at the other day in our homework, was indeed this bubble nucleation exercise. I'm just trying to remind you what the purpose of the exercise was. So this is just my solution to it. Okay. So this was our Ising simulation notebook. And I just added to the Ising simulation notebook a special kind of initial condition. It just initializes a bubble of some size, okay? And so what you can now study in this Ising, among other things, is whether that kind of bubble is stable. So that was one of the exercises. So one of the exercises was to start with a bubble of a given size and to just see whether it tends to grow or it tends to decrease in size. And again, we had that magic formula that somehow says how that should scale with the temperature and with the latent heat and so on. So effectively, the red runs are supposed to be runs where the bubble tends to grow. The green runs are supposed to be runs where the bubble tends to shrink. And the blue runs are runs where it roughly stays the same. You see that numerically, again, every run is different. This is a noisy system. So it requires a little bit of playing around, but you can determine a kind of critical size for the bubble to either shrink or grow. And you can compare this now to a superficially different exercise, which is the following: to take the system. So this is an exercise where I take the system, and so this is an Ising, so it's not a function of density, it's a function of, say, external magnetic field. So I can say make the external magnetic field negative, but initialize with all spins up. That means I'm in the wrong phase. The system should eventually discover that it's in the wrong phase. It should nucleate a bubble, and the bubble should start to grow until I'm in the right phase. Okay. So here I just did a bunch of runs. And again, this is a probabilistic process. So sometimes it happens a little sooner, and sometimes it happens a little bit later. And you can just do this many times and just see on average how long it takes. And on average, the time it takes should go as an exponential in minus the Gibbs free energy of the bubble size, okay? And so this is this magic plot that you can now make. In principle, there's two ways you can determine this. You can determine the probability of nucleating the right phase from the wrong phase, or you can determine the critical size of the bubble. Okay, that should be two equivalent ways of figuring out this nucleation rate. And if the theory is kind of right, then these two ways should agree. And what you see on this plot is that they don't actually perfectly agree. So the solid line is what this exponential would predict, and the two dots are two attempts to determine it numerically from the data. And they don't agree perfectly, but again, this is effectively a log plot where the probability of nucleating the phase changes by many orders of magnitude. So that effectively means that this rate is actually very hard to predict, because it's exponentially sensitive to knowing the right critical bubble size. So you can look at it two ways. You can say that, oh, this is actually kind of poor. My theory is off by almost an order of magnitude. Or you can say that this is a success. You know, it changes by 5 orders of magnitude, and I'm actually within a factor of 5 or 8 or something like this. So it's a tricky business, but at least qualitatively, this kind of bubble nucleation theory is actually kind of okay. So so that was the purpose of that homework exercise. Okie dokie. So yeah, so here's where we are. We're all done with the lectures. As I say, if there aren't any immediate questions, I am available on Friday. We'll have another Zoom session. I would really strongly encourage you to, by that time, attempt all the 4 practice problems that we've now accumulated. And if there's anything that's really at all unclear, then you should really ask